All right, so I want to just hive this off for a little bit and just think about systems of equations. So in order to do that, I'm going to have to add another sheet, and basically that sheet's going to be blank that I'll include as an annotation, and hopefully I can pull that one up. And there you go, that's good. All right, so I've said for many years now, you've been doing simultaneous equations, and simultaneous equations have been hidden away from you because you get something like this for 2x plus 3 is equal to 0, and you do, this is saying find where, there I did it straight away, find where y equals 0 intersects with 2x plus 3. So if I just draw those two lines, y equals 2x plus 3 and y equals 0, this makes much more sense. Okay? This makes much more sense. So if I go ahead and do the solution, just a two-step equation and two undos, then this value here is minus 3 on 2. Now I haven't put the y-axis in because I wanted to show you the simultaneous nature of a very simple solve. Okay? Now, when we come to do proper simultaneous equations, we can do it like this. Okay? So this one here, what would we say? So let's call that 1, let's call that 2. So we've got y equals, it's a little bit less, so I'll just call it y equals minus, it's about a minus x plus 2, and this one would be y equals x plus 1. So we've got the ability to understand what that point is. Now at that point there, they both have the same y value. Y equals y. But I can't solve that. That's silly. But what I can do is I can put it like this and solve this. And that will yield the x value that y equals y sits on. So this is the classic way of doing this from high school. So if I add the apple to that side, you do to one side, you do to the other. If I subtract the 1 from that side, I'll end up with 2x is equal to 2 minus 1 is 1, divided by 2, and so x is equal to a half. So that value there is this one here. So when we put x equals a half into both of these values, we'll get the same result. Now, here's the thing. We're so used to doing things in this kind of way, this formulaic undo. This solution of simultaneous linear equations in foundation maths is a little misplaced in that it's trying to get you to think differently about how you would do simultaneous equations. There's absolutely nothing wrong with doing what I've done there. That's perfectly acceptable. But to treat this in a different way, in a linear algebra way, that's the topic, linear algebra, what we would do is we would take a slightly different approach, and we would put them into a linear algebra form. Now, a linear algebra form is in the form of a matrix. Now, the national curriculum does cover this. It doesn't get covered necessarily in all topics at school in New South Wales, but it does across the Australian nationally. So I'm just going to keep those two in mind. So what we've got is y equals x plus 1, I think that's what we had, and minus x plus 2. And this is where this technique gets a really different approach. So the way that this works is it's going to take the variables and put them on the same side, and then it only deals in coefficients. That's the emphasis. Okay, and I'm going to teach you the most basic way to use them. So what I'm going to do is move the x over here for this one. So I would subtract an x. You do to one side, you do to the other. So I'd have y plus y is equal to 1. Here I'm going to add the x. And so I'll get x plus y is equal to 2. Now I'm going to augment. Now this is this business here, okay? I'm going to augment, and that is I'm going to create an array or a table or a matrix using coefficients. So I don't want you to worry too much about this because this is a 1 question out of 30 questions type scenario, but it is something that will be coming up for you, and it's not surprising that it's in Foundation Maths because they do want to wet your teeth a little bit about it. So if I redraw this, the augmentation requires that. Okay. So they're my variables and they're my constants. These are the variables. And that's how it's treated. And these are constants. Yes, I know you're saying, but hang on, why is not? Okay, when we do this linear transformation, this is the kind of thing that we do. All right, so what I want to do is I want to get to a pattern in the augmented matrix where whatever the other things are, that first one there is a 0. So you're allowed to do row and column operations. So what I'm going to do is swap them. That's the swap symbol. So I'm going to get 1, 1, 2, minus 1, 1, and 1. Very good. The next thing I'm going to do is target this one. I want to make you a 0. How do I make you go away? Well, I treat you like a row or 2 equations, and I'm simply going to add row 2 is going to become row 2 plus row 1. So row 1's not changing, so I'll just put that up. And then row 2 plus row 1. So minus 1 plus 1 is equal to, ta-da, I did it. Right at the next line, 1 plus 1 is equal to 2. So that's now a 2. And 1 plus 2 is equal to 3. So that's 3. So what this allows me to do is it allows me to solve for simultaneous equations. And remembering that I'm going to now I've got that 0 there, I can do what's called a back substitution. Remember that this is the y column and this is the x column. Okay, back substitution. So the rebuild is going to be 2y is equal to 3. Therefore, y is equal to 3 on 2. Oh, so that's where it landed, you see. 3 on 2. Okay, now I've got that, I can rebuild this top one. So rebuilding this top one as a back substitution, I've got x equals 1x. Y is now 3 on 2 is equal to 2. So I'm going to minus 3 on 2 from both sides. And x is going to be 2 minus 3 on 2. That needs to be a 2. So I'm going to 2 on the bottom, 2 on the top. So now I've got the same family of 2. And 2 2s are 4. Same family means that I can do that a half. And that's the same as we had for our particular form when we did it the high school way. So what we're looking at in the next little bit is basically this. Okay, and it's very foreign to you. This is very, very foreign to you because most of you, that means 99% of you, will never have seen anything like this before, and you'll be wondering. But this linear algebra is a subject, actually. It's a subject after Maths 2. It's a second-year subject, and it's wonderful. It's a wonderful lens in which to interpret the world we live in. So I really encourage you not to be overly threatened by this, and we'll see if we can make sense of these particular questions as we go through them. All right, so let's have a look at what's on the sheet keeping in mind that we've got a new way of looking at systems of equations. Now I'm teaching a subject called Calculus 3 at the moment, and Calculus 3 deals in solving systems of linear equations using calculus and all kinds of stuff. So it's very, very interesting. But let's see if we can't use our system of equations in the same way. So we call them unknowns instead of dependents. They can be x and y, but it's really confusing because it can be x1 and y1. The little dashes are usually called primes, and we look for values that satisfy both. Okay, so let's just dive into an example. We may as well use all the 420 metres of fencing and making a new rectangular pen shape. Okay, so if we think about what a pen would look like, it's got a length and a width, and it's got a bar lamb in there. That's shocking, I know. Looks like a puppy dog, doesn't it? Don't trust me, a little tufty tail, that's more like a piggy. But anyway, let's do it. So, 2 lengths plus 2 widths must equal 420. Okay, 2 lengths and 2 widths. Not a T, that's an L. Alright. Now, what else do we know? The width of the length must be 2 to 5, so it's very definitely a width to the length is equal to 2 to 5. Okay, so now to clear the fractions, we're going to multiply by the product of the denominators, and so what we'll get is 5L equals 5L. So those L's will cancel, those 5s will cancel, and so we're left with 5W equals 2L. 5W equals 2L. So when we put the system of equations together, we've got 2L plus 2W. If I minus the 2W, 2L, we'll get 2 minus 2L plus 5W is equal to 0. So that'll be our other equation, 420. So we're replacing the manipulated equation with minus 2L plus 5W. That's 0. Okay. So we just need to eliminate one of the variables by using row and equation operations. And the easiest thing to do is to add one to the other, because minus 2L plus 2L will eliminate. Okay, so if we just add them together, row 1 plus row 2, we'll get 7W is equal to 42. Therefore, W will be equal to 42, because 7 to 42 will be 60. So the width is 60. Okay, 60 metres. And then we can just use that in one of the other equations to solve it. So 60 times 2 is 120. 420 minus 120 is 300. 300 divided by 2 is 150. So the length is 150. So it might seem like in such a simple example, it's you know, a pretty odd way to go about things, but this use of equations in this form, it's introductory. One question out of your whole life is not going to be the end of your world. Okay? Okay. So the systems of equations are given here. So if we think about the width and length, the systems of equations, we've got our 60, 150 there. That's the point. 60, 150, x and y. And length versus width, I think. So that's our length versus width. Okay, so both of our equations, length as a function of will be 210 minus width. I've just remanipulated the equations up here. Okay, and the length of the other one was just a cross multiplication on the fraction. Okay, so one of them has a gradient of -1, there it is. And the other one has a gradient of 2.5. Am I allowed to do that? I don't want to do y equals, but L equals. And there's no b term because it's coming through at 0. See that? There's no +0. And bring these at y equals mx plus b equivalents. Look, it takes practice and time, but what I'm hoping is that you can see that, yes, it's a bit stifling, but it's not really that bad. Okay, it's not like the algebraic gymnastics, that's a bit more difficult. But the word problems are always going to be a challenge, and building the word problems up the way that we are here is doing you no end of help. All right. When we get systems of equations, there's some bigger meta ideas. Meta always means ideas above. Okay, the meta language, the meta ideas, I've taught you a little bit about that. Where they have a unique solution, y equals y, okay, we say that they're consistent. So this is a consistent set. Where they're parallel, they never cross. Oops. So there's no solutions. Inconsistence means no solutions. We'll learn a little bit about no solutions next week. And where they're on top of one another, parallel, every single point is a y. Every single point. So a redundant is infinite solutions. Infinite solutions. So you'll learn that just as an introductory idea. So, of course, what this next set want to do here is see if there's sets of solutions. Okay? See if there's sets of solutions. So, we can use technology to do this. We can take the long way to do it. So we're only 20 minutes, so I think I might just keep plodding along a little bit. Okay. Let's have a look and see what we can come up with, because there's some algebraic interest there. So augmenting each of the equation sets, I'll just do this one first. 2, 1, 7, 3, -1, 8. Okay, so it'd be nice to target any particular one. If I add them together, row 1, row 2 becomes row 2 plus row 1. Then I'll get row 1's not changing. 3 plus 2 is 5. 1 minus 1 is 0. 7, 7, 14, 15. Rebuilding it. So I've got 5x is equal to 15. Therefore, x is equal to 3. To find y, I would put 2x, 2 lots of 3, plus y is equal to 7. That's the other rebuild. So 6 plus y is equal to 7. So therefore y is equal to -6 on both sides. 7 minus 6 is 1. Y is 1. Just check those. Just put them back in. 5, 3 2s are 6. 6 plus 1 is 7. Tick. 3 3s are 9. 9 minus 1 is 8. Tick. So we found the solutions. Okay, so they're intersecting at x equals 3. And they have the y value 1. Put that up there. Put that out. So they're intersecting at that point. It looks like they're both positive, or they're both negative, just less shallow. They're going through that point. Very good. All right, so not too bad, that one. Let's see what the traps are, because that was an example of this one. What's the algebra that uses these? Geometric and algebraic interpretation. Well, we got to this point here, and it was happy days. It all made sense. Let's go and augment this one. 2, 1, 8, 3, 2, 13. Very good. Okay, let's see what we can do here. So if I do the same kind of thing, if I multiply through by 2, if I multiply through by 2, I'll get 2, 1, 8. I just want to demonstrate this for you. So 6, 4, 26. Now row 2 can become row 2 subtract 3 lots of row 1. We can do that. So it's going to be 6 minus 3 lots of 2, which is 6 minus 6, which is 0. So that gives us a 0. 2, 1, and 8 will remain. Now, row 2 is 4 minus 3 lots of 1, which is 4 minus 3, which is 1. And the final one is 26 minus 3 lots of 8, which is 26 minus 3 eighths, 24, which is 2. So doing the rebuild, it looks like we're okay. X and Y, so Y is equal to 2. We read it straight off, so that was good. And if Y is 2, this rebuild will look like this. 2x plus 2 is equal to 8. So subtracting the 2, 2x is equal to 6, x is equal to 3. So let's just check that. 3 2s are 6. 6 plus 2 is 8. Tick. 3 3s are 9. 9 plus 4 is 13. Tick. So they're correct. Those answers are correct. Very good. All right. Well, so far we haven't been too tricky. So augmenting these, we'll get. Oh, now don't like this. So I'm going to rearrange this. Add the 2y plus 2y equals 9. That can stay. 2x minus 4y is equal to 2. Okay, so I'll augment these now. 1, 2, 9. 2 minus 4, 2. Okay, so row 2 is going to become row 2, take away 2 lots of row 1. So row 1's not being challenged by this. 2 minus 4, 2 minus 2 lots of 1, 2 lots of 2, and 2 lots of 9. So 2 minus 2 is 0, great. Minus 2 is plus. Minus 4 minus 4 minus 2 2s are 4. Minus 8, okay. And minus 18, 2 minus 18 is minus 16. Okay, so do the rebuild now. Minus 8y is equal to minus 16, therefore y is equal to minus 16 over minus 8, which is plus 2. Do the rebuild using that. X plus 2 lots of 2 is equal to 9, minus 4, x is equal to 9 minus 4, which is 5, 6, 7, 8, 9. Let's check them. Y equals 2. So up here we can go, here I think is the answer. So 5 plus 4 is 9, tick. 10 minus 8 is 2, tick. So we managed to use the kinds of techniques that the university wanted to introduce you to for this particular type of analysis, and you can do those. And if you learn that, it'll become part of your staple. Now, you get a little introduction in Math 1, and then you hit it pretty hard in Math 2. So there's a little bit of time for you to work it out. All right, the last thing we'll do today, and this wraps up this week for the workshop, is using this version this way. A jazz concert ticket bought for $122,000 on the sale of 7,000. The concert bought in 122,000 for 7,000. If the tickets sold for 10 and 20, how many of each type of ticket were sold? Okay, so we're going to have X is the number of $10 tickets. And Y will be the number of $20 tickets. So now we have to express these amounts in terms of X and Y. Now we know the total of X and Y was 7,000 tickets. So we can write X plus Y. We don't know what the balance was, but we just know that it was that. 10s and 20s sold 7,700 seats. 10s and 20s sold 7,700 seats, so that's pretty easy. Okay, now 10 lots of X, because it's $10 tickets, plus 20 lots of Y came to the revenue amount, 122,000. Oh, very good. 122,000. So now we've got ourselves a set that we can use. Okay, so if I augment this, which is the correct method to do this, we're just dealing with the coefficients. And 1, 7,700. Now I might just divide all of this by 10. Okay, so we'll get 1, 2, and 12,200. You can see now exactly why I did that. Okay, so all we're going to do is row 2 is going to become row 2 subtract row 1. So that's going to make for an easy solution, isn't it? So just taking this up here now. So row 1's not being operated on, so it'll remain at the 12,200 mark. Okay, so 1 take away 1 is 0. 1 take away 2 is minus 1. And 7,700 minus 12,200. 7,700 minus 12,200 minus 4,500. Now it turns out that we can just times this whole thing by minus 1. So we get 1, 2, 12,200, 0, 1, 4,500. So if we unaugment and rebuild, Y is equal to 4,500. So there were 4,500 $20 tickets sold. Okay, 4,500 $20 tickets. So to get the number of X tickets, we just take X is equal to 7,700 minus 4,500. 0, 5 from 7 is 2, 3,200. So there were 3,200 tickets sold for $10. Okay. Now you can do a check if you want to. I'll leave that for you to do as an exercise. Multiply 4,500 by 20 and add it to 3,200 by 10, and you should get $122,000. All right. So we'll finish that one there. A couple of longer videos at the end to wind up with. A lot to digest, but it's about emphasis. I don't want you to be overthinking the simultaneous equations because it's one out of so many questions. You can practice it and take yourself to it, but at least you've had exposure to it and an introduction to it, and that's at least a start for you. All right, the main thing I want you to focus on, people, is the 6 things. okay? And they are the most important things. The word problems and the simultaneous, these systems of linear equations. I would like in a perfect world, we would spend more time on word problems and these kinds of systems equations, but our focus has to be on the 6 things. All right, so nice introduction to those, but we'll leave those there and we'll get on with the 6 things in the coming weeks. Thank you.